Recursion is a term used in programming to describe a procedure in a program which calls itself to get the solution to a problem. Usually procedures will call other procedures to get things done. In this video, I'll describe recursion and give two examples, including one where it sorts an array of numbers. A simple way to describe it is if a game of chess that instead of a piece moving always succeeding in capturing an opponent's piece when it moves to the square it's on, that if there's some contest to decide who wins and who gets captured. In this case, the pieces themselves might end up playing a game of chess to decide who was captured. Recursive code can allow problems to be solved using smaller amounts of code, but they can be harder to understand. I'll give two examples of how to solve problems using recursion now. The first is to calculate a factorial of a number. Factorial of a number is a number multiplied by every integer smaller than it. 3 factorial is 6, so 3 by 2 by 1. 4 factorial is 24, 4 multiplied by 3 multiplied by 2 multiplied by 1, and 5 factorial is 120. If you had a function called integer factorial integer, whose responsibility is to return the factorial of the number that's passed in, then it can be implemented with the logic of if the input is 1, then return 1. Otherwise, I'm going to return whatever number you've passed into me, multiplied by factorial and then input minus 1. So if I was to call with factorial 5, I would return 5 times whatever factorial 4 gives me. And that way it then works its way down the chain. If the function was called with the input parameter of 2, it would call itself passing itself 1 and return 2 times 1. If it was called with an input parameter of 3, it would call itself passing itself 2, and that would then go on and call itself passing 1. The result would be 3 by 2 by 1. Using recursion, it might run into problems that can be hard to predict. If the program has too many function calls, the operating system might halt the program with a stack overflow error. But I guess that would need to be more than 100 calls deep. In practical, it doesn't come out unless there's a bug where a function might call itself an infinite number of times. Another example of recursion is an algorithm called merge sort. Imagine we have an array of numbers and that we want the smallest numbers to be at the left-hand side of the array and the largest on the right-hand side. Merge sort will first split the array into 2 partitions if it can. If it can't, then there's only one element in that partition and it's already sorted. There's nothing further to do for now. To make it simpler, we'll call these partitions queues, the first element of them being the smallest. Now that the partitions are sorted, it then rejoins those queues by comparing the values at the front of each queue and then move the smallest of the 2 off to the left-hand side. That's one level of it, but it needs multiple levels to go through and sort all of the numbers. So the way that merge sort sorts the 2 partitions is a recursive call to merge sort that subpartition. If there was an array with 100 numbers, and merge sort would split the array into 2 partitions of 50. It would then call merge sort on one side, let's say the left, and then merge sort is called on the smaller array of 50 elements to sort. The next level of the call stack splits the 50 elements into 2 subpartitions of 25. The next level splits them down into one of 12 and one of 13, and so on until eventually it will take about 7 levels to go down before the partitions only have one element, and then it starts swapping elements back as they're reconstructed. It then starts working its way back up, and it eventually deals with longer queues to join. Eventually, it'll come back and join the queues we talked about earlier, one of 12 and one of 13, to make a sorted queue of 25 long. With the first half of the 50-element partition sorted, merge sort then goes back down to sort the second half of the 50-element partition. The process of the first half is repeated on the second half, where various size subpartitions are created, split into even smaller partitions, and then rejoined into a sorted partition. The algorithm works its way down and up several different levels of calls to itself that deals with partitions until it finally has the 2 sorted partitions of length 50, and we're back to the level of the first call to merge sort. The last task of the algorithm is to join the 2 now sorted subpartitions into one sorted group together. If you wanted to use a deck of cards to visualize it, here's what I recommend. Shuffle the cards and deal 16 of them face up. Take the left 8, keeping them in the order that they're currently in, and move them slightly left and up in the table, that's your first subpartition. Moving them left and right highlights the partitions, and moving them up and down represents how many times merge sort has called itself. Now take the 4 on the left, that subpartition, and move them left and up again from where they were. Now take the 2 on the left and move them higher again. But the left one goes left and the right one now goes right. With these now sorted subpartitions, it's time to recombine them. So bring them back down to the height of the previous level and swap them so that the smallest on the left. So now you've got your first sorted half of a partition. We take the other 2 cards of that partition and push them higher and to the left and the right, bring them back down, and then swap them as necessary. So the smallest is on the left. We now have 2 sorted partitions and leftmost partition of 4, and we move to sort it. Now compare the smallest card of the left partition and the smallest card of the right, and the 2, and move it down to the left, and then compare the next smallest of each of the 2 partitions until all 4 cards have been moved down a level. Next, move on to the other 4 cards of the partition of 8 and use the same process to sort these next 4 cards, moving them up and down as required. Once that's done, the first partition of 8 is now sorted, and the second partition of 8 is sorted the same way as the first. Finally, the 2 partitions that have been moved up on the table are brought back down to their starting points, and the 16 cards have been sorted. I hope it's been helpful in explaining the concept of recursive functions. I know explaining this would be much easier with graphics, but I'm looking to get more experience in public speaking and create listening practice videos. I'm still relatively new to doing these things here, so please let me know if you have any questions, comments, or feedback. Thanks for listening.